All right, go ahead and get started. So when designing this talk, I thought that they were going to be 50-minute sessions. So what we're going to do is I'm going to go through all the content, but what I've done is I've put everything up on GitHub as well. So for some of them, I'm going to have to skip over the demo portion and just talk about things in abstract. So the purpose of this talk, around Kubernetes 1.0, I gave a talk called Real World Kubernetes, which went through how to manage Kubernetes and how Kubernetes fails. And this talk is kind of updated for 2017 Kubernetes. We now have actually pretty good monitoring systems. We have ways of managing some of the complexity of the system. And so wanted to kind of give an update on where that stuff stands. If you're not familiar with CoreOS, we build a bunch of the open source projects in this ecosystem, introduce things like etcd and container Linux, and then we have products for large organizations and enterprises like Tectonic and Quay. If you want to learn more, you can find out at coreos.com. And so in this presentation, what I'm using, I'm getting a little bit of like echo or feedback on stage. What I'm using to set up these clusters is we have a thing called the Tectonic installer, which installs Kubernetes clusters in a very particular way. This can all be replicated with upstream Kubernetes because, in fact, Tectonic is simply upstream Kubernetes. But just if you want to follow along at home later, that's what I'm doing. So the outline of the architecture or of this discussion is I'm going to talk through cluster architecture, how things fail and how to design for failure, the monitoring and alerting once you've designed out the cluster architecture, backup and disaster recovery, primarily focusing on etcd, how cluster upgrades are approached, particularly with how we install Kubernetes with Tectonic, and then scaling and management of the cluster over time. This is going to be quite a bit, and on a couple of these topics, particularly the scaling and management and disaster recovery, those are quite in-depth topics, so I'll be skipping over most of the details there. So cluster architecture. I like to kind of describe Kubernetes like this. You could, of course, manage a lot of machines yourself by writing like a while loop with SSH and then just kind of doing the stuff and landing the containers. But then what happens when machines fail? There's no monitoring, there's no state recovery. And so we have these machines that we call the master machines that we kind of pull off, and they're the things that actually end up monitoring and maintaining the Kubernetes cluster because they're constantly monitoring and managing the state. Cool. And so at the end, what they're really in charge of is there's a few machines in your cluster that are special, the master machines, and then there's a bunch of machines that are worker machines that take workloads from the master. And then as machines fail, et cetera, or you maybe need to scale up your application over time, that's what those master machines are doing is telling everyone what to do. Cool. So of course, as we all know, those three machines there are actually the Kubernetes control plane, or better known as master nodes. And then on those master nodes, there's a number of control plane components. This includes things like the Kubernetes scheduler, API server, controller manager, etcd, etc. Everything else are just regular worker nodes, or more generically, we just refer to them as nodes. So there's master nodes and then just nodes. Okay, so in today's world, to give you some context on the cluster architecture that we've been going towards with Tectonic, in today's world, the infrastructure and Kubernetes are tied. There's a bunch of tools like kubeup.sh and a bunch of other tools that both deploy the infrastructure and deploy Kubernetes all at once. And so you'd use these tools to like upgrade your cluster or whatever. So a better way that I would argue is that we should be separating out the infrastructure from Kubernetes. So the tools like the Tectonic installer just lay down infrastructure, and then we have tools, in particular Kubernetes APIs themselves, to manage Kubernetes, which means that we're able to use, as I'll show you later, the Kubernetes APIs to say upgrade the Kubernetes APIs. totally reasonable, and I'll tell you why that's totally reasonable later. And the advantage that this gets us is that we can have really consistent experiences across lots of different, a bunch of different cloud providers and bare metal instances and et cetera. Okay, so if you want to try installing a self-hosted cluster that is using Kubernetes to manage Kubernetes, you can find it here. This installer runs on all these different platforms. Okay, all the demos and stuff that I'm about to dive into are at this GitHub URL. My name is spelled with one L, and you can find Kubernetes Day 2. Okay, so the first thing that we want to talk about when we're thinking about Day 2 operations of Kubernetes is, of course, failure, because Day 3 inevitably is going to bring failure. So you should probably start planning pretty immediately. Inside of failure, there's a number of topics. First, we'll walk through the master node failures of the control plane. So again, master nodes, control plane components. The Kubernetes control plane is fairly straightforward. It looks like any other web database or web application you might have ran in your past. There's a data store. There's an application. That application is talked to by clients. The big difference here is that instead of that application, say rendering a blog or something, the application, which is the API server, tells other computers what to do. There's a bunch of different components. I'll talk through some of them in depth, but that's the rough architecture. Primary data store and a primary API server. Okay, so the first demonstration that I'll go through is walking you through a cluster that is self-hosted, where we're actually using Kubernetes to manage Kubernetes. So I'm experiencing a little bit of latency, so hopefully this isn't too painful. But inside of this cluster, there is a number of components that may look familiar. There's a Kubernetes deployment for managing the controller manager. There's a Kubernetes deployment for managing kubedns. There's a Kubernetes deployment for managing the Kubernetes scheduler. And so if you actually click in here, you can start to do super useful things like, figure out from the Kubernetes API, where is the pod that's running, that's the Kubernetes scheduler. Using Prometheus, you can start to find and generate and pull back metadata about how much RAM and CPU and et cetera the components in your control plane are using. All things that you would have had to do anyways. And so it's very good that they are managed in this way. So that's the big idea, is that we're managing all these things, whether it's the daemon, the API server, which runs as a daemon set for a variety of reasons, or the API or the scheduler, or the networking system, which runs as a daemon set, et cetera. All these things are managed as part of Kubernetes on Kubernetes. Everyone get it? Can I get a show of hands if it makes sense, what's been shown so far? Okay, cool. Okay, so that's the high-level concept. Now, the one little fly in the ointment here is that we also have to run a database. And can I get a show of hands of who's ran databases on Kubernetes? Okay, so a lot less confidence there. So what we've built, well, I'll walk through etcd. So etcd is a little bit special. A lot of applications that are really easy to deploy on top of Kubernetes are stateless apps, but this is a stateful app, which means that all the on-disk state is unique to the node that it's running on. etcd is useful, and the reason that Kubernetes uses it is because it's clustered and fully replicated. You can think of it sort of like RAID for database, in that every write ends up getting written out to a bunch of different replicas at the same time. And then it requires a 50% plus one availability to do any writes into the data store. So what that means for us as people who have to operate this database is that we need to ensure that it's monitored and that we recover if any of the machines go down as quickly as possible. This is generally why the recommendation is of 5 nodes, because you can have one I tripped over the power cable moment, and then also the hardware randomly failed moment, and still have 50% plus one. Okay, so what we've done is we've built this piece of technology to help operate etcd on top of Kubernetes called the etcd operator. What happens in practice is that you can actually go and ask Kubernetes to essentially have a special resource, etcd cluster resource. So I think it's cluster.etcd, which says things like the cluster size, which version of Kubernetes, or which version of etcd to run, etc. Dang, latency's killing me. So you see here that inside of our namespace of kube system, we have a kubeetcd, which has a number of events and then a cluster size and a particular version. And so what this etcd operator does is it sits there sort of like the controller manager for other components in Kubernetes, and it observes and essentially runs this reconciliation loop of state. Is the cluster in the state that it should be? I'll observe the current cluster state. I'll analyze, well, the user said to run 5, but only 4 are running, and then act. It'll say, well, in order to get back up to 5, I need to add another 1. This whole thing is open source and is really slick for running etcd on top of Kubernetes. What I'm going to show you next is that we're actually running it both on top of and underneath Kubernetes, and I'll show you why that's safe as well. So in order to survive a failure of etcd, you need to do a few things. You need to tune etcd for network latency. Etcd relies on being able to know that a given round trip to any of its peers happens within some time bound. You need to maintain that 50% plus 1 availability. You need to ensure that there's persistent disks. If a node goes away and comes back, the same data should be there. This is true in pretty much all cloud environments, at least on a single machine, and that's sufficient for etcd. For disaster recovery, we have an out-of-bound tool called etcd snapshot, which you can use to snapshot the data store and back it up to wherever you want to back it up to. And then the etcd operator natively can do things like backup etcd snapshots to S3 on a schedule. So I want to show you this demo that I did last night. The reason that I had to record it is because I'm using Amazon auto-scaling groups, and I'd rather not spend 15 minutes of us just watching a spinner, even though it might be entertaining. I don't know, it's the last day of the conference, maybe that's all the brain power we have. But what I have here is, this is the exact same cluster that is running here. It's like an 8-member or so cluster on AWS. Yeah, so if we dive in here, there's 5 master nodes, and then there's a few worker nodes. And then on each of these master nodes is a etcd, a member of etcd. And so what I'm going to demonstrate is I'm going to go in and just confirm that etcd is 5 copies of etcd are running. They're running across unique 5 different machines, and I'll talk about how that's possible later. And I just choose one of the machines that etcd is running on, and I just terminate it. What this will do is that the machine will shut down, and Amazon will permanently delete that. And what will happen pretty quickly here is that we'll see that this node will be just removed from the node list as the health checks expire inside of Kubernetes. By default, it's like a 60-second timeout or something. And what will happen is that once that timeout is reached, the pods will get unscheduled, get removed, and eventually be marked as terminated. And once they do get terminated, the etcd operator was going to get agitated. It's going to be like, what? I had 5 running, and now there's only 4? I need to take some action. And so what will happen is Amazon will launch the new machine, and in the meantime, this is really important. I'll roll it back just a smidge. Etcd operator has said, please run another copy of etcd. I'm currently out of spec. But Kubernetes has a constraint that says I can't run etcd on the same machine. And so it'll just sit here unschedulable until the new machine comes up. And then once the new machine comes up, it goes into readiness, it gets scheduled to the machine, The machine downloads a new copy of etcd software. It gets replicated, the data from the existing cluster, and we're back into a healthy cluster state. And this is all possible through two reasons. One is that the etcd operator is essentially acting and acting out all this operational knowledge of how to add and remove machines, members from the etcd cluster. And it's a single piece of software that's running on top of Kubernetes that's leader elected. So we're essentially relying on its ability to make decisions. Cool. So that is kind of the vision that we have for the near future here. This is all this self-hosted etcd, and managing this database this way is something that's inside of Tectonic Installer right now and works against 1.5. And it's the way that we'll be essentially installing and managing etcd over time in the coming weeks and months. Any questions on that? Yes?
Does the etcd use persistent volumes underneath for the storage, or just the ephemeral storage of the instances?
So the question was if the etcd instances are using EBS or ephemeral storage. I'd have to look. I don't know in this particular configuration. As long as the machines are able to reboot and have the same state, it's fine for etcd.
When you are recovering a node, do you take a snapshot from the healthy?
So when we recover a node, the way etcd works is that when the nodes come up, they essentially tell everyone what the latest version of the data store they have, and then one of the machines, not the leader, will catch the other node up. It works very much like RAID, essentially. Great question. Yes?
So since you're running self-hosted Kubernetes,
Yeah.
is there any reason to mark the nodes as master?
Yeah.
It could run anywhere.
Yeah, so the reason that we mark, the question was, is there any reason to mark the nodes as master? So we have this label that we put on all the nodes that says master equals true. The reason that we do that is because we want particular workloads to land on the master nodes. And it allows us to do things like anti-affinity calculations. The reason that you might want to do that is because your master cluster should be more or less static and only be running a set of workloads. You probably don't want your master workload to also be running your application, because if somebody works their way back out of your application into your master node, you're going to have a bad day. And the other reason is you can put them in separate auto-scaling groups, or you can manage them differently. You could manage your workers based on demand, but you kind of want that core set of nodes to remain more or less static.
There is a way to mark these nodes as priority, right? I forgot what the annotation is, and then Kubernetes will not delete them first in case of a resource constraint.
Correct. Yeah, there are ways of essentially ensuring certain workloads land. This is mostly about operationalizing it, knowing which nodes to monitor, having them of different size, et cetera. Cool. So that's node failure and discovery. There's a couple other demos that I recorded. One is about scaling it up. So this cluster started off as a single member cluster, and then I scaled everything up to a 5-member cluster, and the etcd operator helped me scale it up. You can also scale it back down, et cetera. Okay, so the next piece of thing that you need to worry about is the API server. This one's a lot easier. It's stateless, it's etcd backed, it's horizontally scalable. You can just add more to get more read capacity. It does require a load balancer, and this is for a few reasons. One is that as a command line tool, or if you're interacting with a graphical console, you need a single point to interact with it. The other reason is that the sort of discovery endpoint inside of Kubernetes is kind of broken right now, and we just need to fix it upstream. So hopefully in the future, this load balancer requirement goes away, but it is what it is today. So surviving failure of API server is pretty straightforward. You want to run in API servers generally to match your etcd count, because the API server is essentially relying on etcd as its primary data store. And if you think of the API server as like a read cache in front of etcd, you kind of want to have a one-to-one mapping. You also want to match failure domains. Generally, all these systems are designed for single machine failures to be okay. And so you want etcd and the API server to be resting together, because etcd is useless without the API server in the context of Kubernetes, and the API server is useless without etcd. They're really the require each other. And then monitor and maintain load balancers over time. So The cool thing that we can do with the self-hosted stuff is we can actually just come in and fail individual API server nodes. So I can come in and just delete this pod, it'll end up getting terminated, and then Kubernetes will recover from it. Now, one of the questions that I often get asked about this is really recursive, I'm a system administrator, I want everything to be stable, isn't this really unstable? The way the whole thing is designed is that just like any other system that is executing processes under Linux, we persist things to disk. So when we think about the API server, or we think about etcd, we have a piece of software called the checkpointer that takes what the node should be running, and then we persist it to disk. And then when the node comes back up, it launches those things even in cases where it can't talk to an API server. And so we're able to essentially have Bedrock be on disk. And that's the way that we make all these operations safe that I'm demonstrating on top of the cluster, using the cluster to manage the resources. It's no more or less different than having like an init ramfs that has systemd services that then are launched later, if that makes sense. Okay. Cool. So what are the risks? Like, what are the risks if you don't maintain the API server in etcd? If your etcd cluster goes below a certain threshold, below 50% plus one, it will go read-only. So you won't be able to do any posts, which means that your cluster is fine. Kubernetes clusters will continue to run their workloads if they're unable to talk to the control plane. What you will lose is cluster visibility, because a lot of things like events and stuff get pushed through etcd. And you may lose the ability to find and do service discovery. However, DNS should be cached. So as long as your DNS instances, your kubedns instances remain running, you aren't at risk of DNS starting to fail for inter-cluster service discovery. Okay, so the next bit are the scheduler and the controller manager. So the scheduler and controller manager are stateful, but they back their state with the API server. So to a large degree, what happens is that if you lose a scheduler or controller manager, they will take a few seconds to come back up because they need to rebuild internal state, and then they rebuild that internal state from the API. They're leader elected, so it's totally safe to have multiple copies of these, but they're not horizontally scalable. Adding more schedulers or more controller managers does not make the scheduling faster. I wish that's the way that worked, but that's just simply not the case. And it's totally possible to recover from mistakes. So if we think back to the API server in etcd, I said that we persist these things to disk. We don't persist any of the other Kubernetes components to disk. But it's okay, because the scheduler and controller manager, if you screw up an update or you accidentally scale your scheduler down to 0, you can recover from that, and I'll show you how. So you can run, like I said, you can run 2 or more copies, but they're leader elected. You need to have anti-affinity to ensure that you survive any single machine failure. So imagine that you have the scheduler, you have 2 copies, but they're running on the same host. That's not actually going to help you when that host goes down. Okay, so this is a pretty quick demo, so I'll show you this. What we'll do is we'll scale the kube scheduler down to 0, which means that essentially we're simulating a outage where we lost all the machines where the scheduler was running on, and now no new forward progress can happen against Kubernetes. Okay, so the Kubernetes deployment for the scheduler has been scaled down. Now we have a problem. How do we schedule our new scheduler? Anyone have an idea of how we might do that? So what?
You deploy a recovery scheduler.
Yeah, exactly. So you, what you do is you get the deployment of the scheduler. So, and then you act like you're a scheduler yourself. I think I can figure out the name of a node to place the scheduler on. I'm a pretty smart guy. I can choose randomly from a list of 6 options. So I'll show you how that works. So you take the scheduler, you get the deployment object because the API server is still running. So I go in and I look at the scheduler object. The first thing I have to do is I have to change the kind from deployment to pod. I can delete most of this stuff. I'll keep the namespace and the name. And then the spec mostly deals with the deployment stuff. But inside of here is the pod template. So if I come in here and just delete essentially everything else that's not the pod template, I move this around, and now I have pod, a single pod. And the last thing that I need to do is just choose a node. So if I go in and put a node name, and I need to get the name of my nodes, choose one of, it's not master, it's true. So I need to find a node that's obviously a master, so I put it on one of the correct machines. And then I can just do kubectl create -f. And what will happen is that I now have a scheduler that is running back on the machines. And then if I want to scale my deployment back up of schedulers to 2, that will happily happen, and I can delete my scheduler. So in the face of scheduler failures, your worst case scenario is that you have to act like a scheduler for a second. But I have confidence that each and every one of you can do that. Okay. The other thing to keep in mind about the scheduler and the controller manager is that there's failure risk. The controller manager, if it goes down, you will lose cloud provider integrations. You won't be able to spin up load balancers or attach persistent disks. If the controller manager and the scheduler go down, you won't be able to do deployments. You won't be able to scale, as I just demonstrated. And then failed node workloads won't reschedule. So if that auto-scaling group, like I had shown, if I had nuked that machine, when the new machine comes up, it won't actually get scheduled new workloads, and the old workloads won't get unscheduled. So that's your risk. And generally, that means that you can have like anywhere from 5 minutes to hours to respond to these components inside of Kubernetes going down. The last bit is DNS. I like this haiku really well. I used to work on DNS early in my career. It's not DNS. There's no way it's DNS. It was DNS. I think we've all experienced this for ourselves. So Kubernetes DNS is a little tricky. Pretty much everything else in Kubernetes can use service discovery. But the reason this haiku is so applicable is because everything relies on service discovery. And so the Kubernetes DNS service lives at a predefined service IP. And so you have to run this service at that IP all the time. But the risk is really low of the DNS going down. It's used by many applications, the kubedns, but it's not used by kube itself. So if it goes down, your applications may stop responding, but you still start to recover your cluster and reschedule a new DNS server. All right, the last bit is around nodes, the places where the actual user applications work. Labels are really flexible. So with labels, we're able to say, make selections in a variety of ways, maybe front end and back end, or based on user, or based on environment. These same labels can be used against nodes, and this is really useful where we can start to say, this node lives in this particular rack, or this node lives in this particular region, or this node lives on this particular switch. The way that I've been demonstrating all this stuff with etcd and the API server, et cetera, is that I've been using a concept called anti-affinity, which is really important to ensure that your applications end up spread out across your clusters, and you don't accidentally end up failing your application because all 20 of your horizontally scaled apps landed on one node. So this is a feature called failure domains, which is in beta. And it uses labels, like the rest of the system, to decide where to land workloads. So again, you can start to break up your system based on node labeling. So a quick demo that I wanted to give was kubectl has this really great thing called JSON path that allows you to query through the cluster. So you can get nodes. Let me see if I have it in my, there we go. So what we'll do is we'll look at this thing called the failure domain region, which is automatically populated by the cloud provider integration. So in this case, it lists all the AWS regions. And then there's also failure domain zone, which lists the actual availability zone. So you can start to partition, and this is how like the etcd operator partitions stuff by default. Cool. And then it's all just wrapped up in this node selector and then a topology key. So in the case of etcd, we say ensure that things that are labeled etcd cluster equals kubetcd don't end up in the same topology, like each node doesn't end up in the same topology where the host name matches, because we don't want them to land on the same machine ever. All right, so I have 5 minutes left and 5 sections. This is going to go super well. Monitoring and alerting. So nearly all components have metrics APIs that are in Prometheus format, and it's primarily what this means is there's a metric, there's a label, there's a value, and then optionally a timestamp. We, of course, have built this thing called the Prometheus operator, which is also open source. You can find it at CoreOS/Prometheus operator on GitHub. One of the things that, kind of the last thing I'll demo here is this thing called Kubernetes, which folks from SoundCloud have built a bunch of rules that allow you to let me see, scale, which allow you to monitor and have best practices around alerting of the health of Kubernetes. So it has best practices around API server, the scheduler, etcd, et cetera. You can see the README for how to deploy it, but I've deployed it on this cluster. So it can do things like look at the node status and tell you like, oh, a bunch of nodes are down and give you an alert. So example, this query will say, if there's more than 10% of my nodes that are in non-node ready, send me an alert. And it could go to PagerDuty or email or whatever. And the other piece that it has is it'll start to scrape metrics, CPU network storage metrics from individual nodes so that you can start to alert on, hey, RAM usage is at 80% full or whatever. So this is an example of a query that is provided in Kubernetes to say, give me the used percentage of Kubernetes memory versus currently consumed memory in our pods. And you can also start to drill down and say, give me the container memory that's used by individual applications like Node Exporter. So the most interesting thing, I think, is how do you monitor the control plane? So in this repo, there's rules around ensuring that etcd is remaining up with that 50% plus 1. Checks for high churn of leader election, perhaps you're having a network problem, and then also API response times. The key metrics that you need to look for thinking about the API server is essentially latency and the etcd latency between the API server, and then also scheduling latency. Our nodes or our pods getting scheduled on the order of minutes or hours or days, something that you need to keep an eye on. The last bit is around apps. So the Prometheus operator lets you use label queries to find and discover and monitor your applications as well. All right, so disaster recovery, you can read the README on the notes that I have on GitHub. Cluster upgrades, this is really where self-hosted shines. So there's 2 vulnerabilities that happened on October 20th, 2016. There's Dirty Cow. Who was affected by Dirty Cow? Everyone, I hope. Probably everyone's phone is still unpatched. And then there's also a Kubernetes client cert validation problem, which I gave a name. It didn't catch on, called Mask. Capitalize the K because Kubernetes. But the cool thing about this is that we're able to start to do things like upgrade and downgrade all the components in Kubernetes via the Kubernetes API. So that scheduler deployment, we can just swap out the container that's currently at 154 and bump it up to 155, and then watch and use the rolling upgrade capabilities of Kubernetes to handle that operational concern. All right, last bit is management of nodes. Not going to cover it, but essentially you can use, with all this technology, auto-scaling groups or Terraform to kind of statelessly manage the nodes and then rely on Kubernetes to manage the state of the Kubernetes application. All right, so try to get one more demo in, but if you want to try this stuff out, again, go to github.com/phillips/Kubernetes day 2, and you can try out some of the demos. If you want to get a cluster running, check out the Tectonic installer, and you can kind of play with everything that I've been showing off today. I want to thank you. I want to try to get, we can do the applause thing, and then I'll try to get one more demo. All right, thanks. So let's see if this works. It didn't work. Well, there you go. All right. Well, I have like 1 minute for questions if there's one more question. Yes?
If etcd goes below quorum, is the operator still able to schedule another node to replace it, or are you screwed then?
Yeah, if etcd goes below quorum, you're kind of screwed. You have to, you're actually in disaster recovery mode, and you have to restore from backup. The backup will be really up to date. It'll be, because everything's been read-only for such a long time, but you have to actually go through and take manual steps, because only a human being can make decisions at that point. It's sort of like the scheduler problem. Once you go below quorum, the computer can't make a reasonable decision, so a human has to step in. But there's a disaster recovery guide on etcd for handling that. Yeah.
Issue open for etcd operator to support TLS?
Yeah. So the question was about etcd operator and TLS. That will be supported probably in the next release or two. Yeah. All right. Thanks so much. I don't want to like take the room, but I'll answer questions outside. So thank you.